Hello Primary 5 students. By the way, in this lesson, you may be feeling attracted a little bit to your chairs. This is because we are going to study Unit 1, Energy, Lesson 4, Magnetism and Electricity. So let's take the flight! Who remembers from last year Primary 4, we studied the types of energy, and one of these types is the electricity or the electric energy. The electricity is a type of energy that's coming out from a battery. It causes the devices to switch on. Like here in the picture, when the circuit is open, there will be no electricity moving in the wires, so the lamp will switch off. But when the electric circuit is closed, the electricity will move through the wires to switch on the lamp. So during this lesson, we are going to prove together that electric current has a magnetic field and the magnet generates electric current. Okay, if you get two electric wires and connect them to a battery and connect them to a compass, you will observe that the compass needle will move or deflect. Do you know what's meant or remember what's meant by deflect? Yes, deflect, it means moves. What causes the needle to move? Actually, generating or presence of magnetic field causes the movement of the magnet, as you studied in the previous lesson. So, there must be a magnetic field produced or created by the electricity moves in the electric wire. So, scientists discovered that from electricity we can generate or produce or create a new magnet. This magnet is called the electromagnet. Electromagnet. It means from electric to magnetic. Electro from electricity to magnets.
I have a wire that goes through a piece of cardboard here, and I've got it surrounded by little tiny compasses. They're all pointing generally this direction. And I'm going to run current through the wire that will be coming up the wire this way from underneath. So based on the right-hand rule, there should be a magnetic field around this wire. In which direction? Let's find out. So I'm going to clip this on now. So it looks like all of the arrows are tending to go around in a counterclockwise fashion from this perspective. I'll turn the current back off. Now I'm going to reverse the current and run it the other direction. So in this case, the current will be flowing down the wire through the cardboard. And let's see what direction the field is there. And now they all seem to be pointing in a clockwise fashion around the wire. The farther I get from the wire, the weaker the field seems to get. I didn't quite line up as quickly or prominently. I'll pull them back a little farther. So they're all being influenced by the Earth's magnetic field there. And they're not all pointing perpendicular to the wire anymore. They're being more greatly influenced by the Earth's field. This one was having a real hard time deciding, is the Earth's field stronger or is this one stronger due to the wire? Let's do a little farther out. There we are. One more try. Kind of a tepid response from a few of them. This one ended up pointing that way. The Earth's field is pointing this way. The wire is trying to point the field that way, and I end up getting some sort of strange component that ends up pointing away from the wire. It's trying to hook around, but it's not doing a real good job. So the field strength drops off dramatically with distance. We'll have to determine mathematically if it drops off as 1 over r squared or 1 over r or some other relationship. But it's definitely stronger close to the wire. The magnetic field around a current carrying wire.
So the electromagnet is a temporary magnet which is made by the effect of electricity. And temporary, it means for a while, not permanent. It means for a while or for short time. So the electromagnet is a temporary magnet which is made by the effect of electricity. It consists of a bar of wrought iron, a copper wire coiling around a bar of iron, and a dry cell. So let's make a small experiment together. Get your ingredients together, which are a bar of wrought iron, a copper wire, and a battery or dry cell. And shall we create a new magnet? Let's go. So how many paper clips did your electromagnets attract? 1, 2, 3. Okay, who wants to attract more paper clips? Well, for this purpose, you will use some small tips. The first step is increasing the number of coil turns. The second step is increasing the number of batteries or dry cells to increase the electric intensity, so you will have a stronger electromagnet.
Take a long coil with many circular turns of insulated copper, wrapped closely in the shape of a cylinder. This type of coil is called as a solenoid. The electromagnetic effect of a solenoid is used in several appliances. Let us pass electric current through the solenoid and observe the pattern of magnetic field lines demonstrated here. The magnetic field lines in a solenoid are same as in a bar magnet. They pass through the solenoid and return from the other end. The field lines inside the solenoid are parallel to each other. The parallel lines will have the same magnitude of the magnetic field. That is why the solenoid has a uniform magnetic field. If we suspend this current-carrying solenoid freely, it rests pointing north and south, just like the suspended magnetic bar does. It shows that on passing electric current, the solenoid turns to a magnet having north and south poles. When we take a piece of soft iron inside this coil, the iron piece is pulled inside. The electromagnetic effect performs the mechanical function of pulling. The system of a coil with soft iron core is used for several electromechanical applications, such as start or stop actions for valves of the dishwashers, starters of vehicles, pull and push agents of the door locks, etc. The current-carrying solenoid converts the soft iron into an electromagnet. When the current is stopped, the solenoid is demagnetized. Even the soft iron core also loses its magnetism.
So keep your mind. Give reason. It's better to increase coil turns number in electromagnets. Or give reason. Increasing number of batteries is preferred in electromagnets. The answer will be to increase the magnetic field in electromagnets or to make them more stronger. Definitely, electromagnets are very important in real life. They are used in factories to lift the heavy iron trash or iron blocks, as they are used in making cranes or winches. Secondly, it's important in making many home appliances like the electric mixer, electric bell, disk drive, and TV.
Don't make me get.